quantum and classical deterministic, and then later quantum and classical randomized, right, in terms of query complexity. However, those problems were some or the other kind of promise problems, right? That is, there was some promise given on the input. Simon, some promise given. Teuscher's problem, some promise is given, right? Teuscher's a problem whether it is a balanced function versus it is a constant function. It is not the case of that any given input, any given string is there on the input, right? You are always promised that the input string is of some type, this type or that type. So now we will see advantage now for a regular problem, not a promise problem. Okay. What is known as a total function, right? That is, the function is defined on every string. Okay. Now what is it? Okay, this is actually now a search problem. What is a search problem? We have database where we have, let's call capital N as 2 to the n, okay? 2 to the n different bits are there on the database, okay? And we want to determine location of a 1. Any one, any place where the bit is 1. Okay, any place where we have a 1. So every place there is either 0 or 1, something like that. We have to determine any one place where there is a 1. Now in particular, take the case where suppose, so this is a hard instance, suppose everywhere it is zeros but only one place it is 1, okay, only one place. But the 1 can be any places among the 2 to the n possible different, 2 to the small n, capital N possible places in the database, and we need to determine where it is. So if we try to do with classical algorithms, even classical randomized algorithms, you know, out of the 2 to the n different locations, I have to spot a 1, okay. Even if I pick randomly, it will not help me, okay. Okay, this is not the place where I will get the, you know, advantage of the birthday paradox even, okay. So I will really have to look at close to 2 to the n locations, like omega of 2 to the n. Okay, constant times 2 to the n we have to look. Okay, now we will see that in the quantum case we can do with 2 to the n over 2, that is square root of capital N. In the classical case, even classical randomized, we need omega of capital N. In the quantum case, we can do with order square root of capital N. So now you see the difference, quadratic advantage, capital N versus square root capital N. Agreed? Now we will see that mainly this advantage is coming from the L1 versus L2. Okay, as we proceed, we will observe that this advantage is coming from this difference of L1 versus L2. Okay, but let's look at it. Okay, so the problem is clear what we are trying to solve. Good, that is the Grover's problem. You are given a function f, find an x such that f of x equal to 1. Okay, the string in the database is represented by f. X represents the location. So we need to find a location where f of x is 1. Fantastic. Now let us get into the algorithm straight away. Okay, algorithm. All right. So first let us define the set of string A where capital A, all the locations x where f of x is 1. So all the locations where f of x is 1, that is what we are calling capital A. And the number of such locations we are calling small a. Agreed? Very good. Let us define this vector capital A, which is the uniform superposition of all x in A. Agreed? Let us define that vector. Uniform superposition 1 over square root small a, because there are small a such entries, summation x in capital A ket x. Agreed? Simply we define this one. Now also define B. What is B? Capital B? All the locations where f of x is 0. Number of such locations small b. Define ket b as 1 over square root b summation x in b ket x. Defined? Any questions? Any issues here? Just we are simply defining this ket a, ket b. Okay, very good. Long press. Is it there? You can see the light?
Yes.
Yeah. Yeah.
Is that definition in sync with the probability of getting a ket x is that 1 by root a whole square, something like that, or is it just a definition keeping in mind some algorithm? So
No. Yeah. No. If you're going to measure this state a ket a, and you will obtain x with probability 1 over a. That is correct.
whatever probability we get, that they are calling it as 1 over root a. Is that
No,
correct,
not
sir?
the whatever problem. Don't even go into probability for now.
Okay.
Simply think this is a superposition state, right? We just define it. What will happen if we measure and all, we'll get to that later on. But we can see one thing. If I am at this state, ket a, suppose I reach this state ket a, and if I go ahead and measure, what x will I get? Any x in capital A with equal probability. Agreed? But only those I will get. I will not get any x in capital B. Will I get? That one has probability 0 there. So therefore our intention is to reach capital A, because once we reach capital A, we measure, and one of the any location we get has a 1. Correct? So our intention is to reach capital A. Start with our algorithm will start with ket zeros. We'll have to do something so that we reach capital A. Once we reach capital A, we measure. That is our intention. Clear? Even if we reach capital A or even near to capital A, it's still good. Because if we reach capital A, with probability 1 we will get x in A. But if we reach near capital A, with high probability we will get x in A. With small probability we will get x in B, but other than that, with high probability, very high probability. So our intention is to be very close to A, ket A. That's all. Agreed? Any questions? Yes? Any questions? Good. Now, that is the thing. Right. Now let us, as I said, capital N is 2 to the n. Agreed? Capital N is 2 to the n. Is this big enough or, yeah, visible? Okay. Now, let us define this uniform superposition over all x that we have seen so many times already. All strings x is 0, 1 to the n ket x, normalized by 1 over square root n. Agreed? How do we create it? We simply do a h tensor n on 0 to the n. Correct? 0 0 ket 0 0 0 0 n times. We do h h h h h h. We create uniform superposition. This we have seen a few times already. Agreed? Any questions here? This we can create, not a problem. Agreed? Uniform superposition over all x. There we are not worried about which x has 1, which x has 0. All x. Very good. So our algorithm will be as follows. Okay. Now let us look at it pictorially. Okay? Pictorially. This is our algorithm. Pictorially. What do? Remember, we have defined ket A and ket B. What is the inner product between ket A and ket B? What is the inner product? Somebody said 0. Correct. No common string. If you use the formula for inner product, there is no common string only. Wherever this has a amplitude, this is 0. Wherever this has amplitude, this is 0. Agreed? And because of our normalization, they are both have L2 norm what? 1. Agreed? Because we normalize by 1 over square root A, 1 over square root B. L2 norm is 1. Plane spanned by the two vectors. Okay. Now in that plane, every vector is a linear combination of ket A and ket B. Agreed? Very good. Now what happens? Look at this uniform vector H. Remember this H we are calling uniform superposition here, right? This uniform superposition vector is a linear combination of ket A and ket B. Yes? How do we write that one? Do you agree? Yes? See, this one is summation over x in A. You multiply by square root A, what do you get? Summation over x in A. Agreed? Then this one you multiply by square root B, summation over x in B. If you do summation over x in A, summation over x in B, what do you get? Everything. Yes? All locations you will get, right? Then you just divide by 1 over square, because you will get this, and then you will divide by 1 over square root n. Agreed? Yes or no? Simply we are multiplying ket A by square root A. So we get this summation. Multiply by square root B, we get this summation. We add the 2, we get this. We divide by 1 over square root n to get ket H. Agreed? Okay, very good. So we observe that ket H is in the uniform, is in the plane of ket A and ket B. Agreed? It's a superposition, some linear combination of ket A and ket B. Agreed? Very good. Now what do? Remember, we said that we can start with ket H, not a problem, correct? We can start with ket H, not a problem. Agreed? Because ket H is simply all zeros, hard one, hard one, hard one, hard one. Now what do we do? See, ket h is actually, if we observe, we don't know, but it is possible that ket h is maybe very close to ket b. It is possible. We don't know. Then we have to somehow take it to ket a, around ket b, by ket h, around ket h. Then V3 we again reflect around b, go to V4. V4 we reflect around h, go to V5. This way we are going closer to A. Agreed? This alternate reflections around ket B, ket H, ket B, ket H, ket B, ket H. Okay? This is our algorithm. Now, okay? Now you see one thing. Let us say our starting angle is theta. Starting angle between H and B is theta. Then once we reflect, where we get V2, which is also theta here. Agreed? Now, then we reflect around H, we get here 2 theta, right? Because this is theta, reflect around H, we get 2 theta here. Agreed? Then what do we do? Reflect about B again. So there is this theta already. This is 2 theta plus theta, so 3 theta. So this is 2 theta, theta plus 2 theta. We reach here. Then we reflect about this. This we reflect about H. So 2 theta plus 2 theta, 4 theta, 2 theta, 2 theta. Agreed? So what is happening? After these 2 reflections, we are always pushing it by 2 theta. 2 theta, 2 theta towards A. Okay? Good. Now let us see how many iterations we will need to get close to A. So for that we have to determine what is theta. At least get some sense of what is theta. Any questions? Any questions?
So could you repeat how did you get H?
Ket H.
Sure.
Ket H is uniform superposition over all strings, all n-bit strings. Agreed? Yes?
So like could you just elaborate a bit?
What is Ket H?
Yeah.
Ket H is this.
So you said that it derived from ket A and B, right? So that part I didn't understand.
Oh, how did we derive Ket H from Ket A and Ket B? Okay. Okay. This definition of Ket A is clear to you? Yes? Now what is square root A times Ket A?
So it's like the sum of all the states in which there is no 0.
Summation x in capital A, Ket X. Agreed? This one. What is square root B times Ket B?
Like summation of all the states having ket 0. Yeah.
Fx equal to 0. Agreed? Summation x in B, Ket X. X in B. What is capital B? All x such that f of x is 0. Now, if I add this square root A times Ket A plus square root B times Ket B, what do I get? Huh? Do I get this? Summation over all x? Because there are only 2 possibilities. No, f of x is 0, f of x is 1. Correct? Do I get this? Then I divide by 1 over square root n. I get Ket H. That's what we are doing. Square root A, Ket A plus square root B, Ket B divided by square root n. Clear?
And so like how is that Hadamard, like from where that is coming? Hadamard.
The Hadamard, remember the formula? Formula for Hadamard. Hadamard tensor n on 0 n. What was this? Summation over x this is the formula. You remember this one? That is only. So how do we get this? Simply start with n zeros, do Hadamard on each wire. We get this. That is this.
So like it's basically that the formulas matched, right? But was there any logic behind it? Like we know that Hadamard ket 0 power n is the formula of this, and we got that ket a plus, or maybe that f of x equals 0 comma 1, that sum of all states as the same. But is there a relation between them? That's why we got the same formula.
Sorry, what relation are you talking about?
So
No,
like
look, we want to create this uniform superposition over all x, right? So we create it via this. I'm not sure if I understand your question.
So like over here, the formulas of Hadamard ket 0 power n and the formula for ket h are matching, right?
Formula for
Ket h.
ket h, matching.
Okay. So was there a reason behind it? Because we just mathematically said that this is same as that.
No, reason behind, because that is what we defined. We defined ket h to be the uniform superposition. Correct. We defined ket h to be the uniform superposition. We defined ket h to be this. There is no reason, we just define ket h to be this. Once we define it, it is what it is. We just using shorthand ket h for this. Correct. Ket h is just the shorthand for that. Agreed? Any more questions? Yes? Good. So therefore, now let us get a sense. See, so this is the algorithm. Start with ket h, alternately reflect about ket b and ket h. After k iterations, angle of v 2k plus 1 with ket b becomes 2k plus 1 theta. Agreed? It starts with theta, each time you add 2 theta to theta. So it becomes 2k plus 1 theta. Agreed? Okay. Now, what is theta? That is, let's try to determine that. Okay? What is theta? Okay. Firstly, we can note one thing, trigonometry. If we define theta in radians, not degrees, radians, then for small theta, theta is very near to sine theta. You know this? For small theta, theta is very near to sine theta. Because if you look at the Taylor expansion of sine theta, the first term is theta. After that, there are lower order terms. Okay? Agreed? Yes? So theta is like sine theta. Okay. Another thing, okay, this maybe we can do sometime in tutorial. You can take it as homework exercise. If I have two vectors, okay, v1, okay, suppose they are both normal. Agreed? This you can take it as homework exercise. Later also we can try to do in a tutorial. Okay? This one, I don't know if you are able to recall from your trigonometry or not, but you can try to refresh this. It's beta cos beta is given by mod of the inner product. Okay. I am talking about for now angles less than 90 degree. Okay. Any questions? Yes. Okay. Now using that formula, what do we know? Theta is the angle between ket h and ket b. Agreed? So if theta is the angle between ket h and ket b, that one becomes cos theta equal to mod of the inner product between ket h and ket b. Agreed? Yes? Very good. However, we need to find sin theta. Correct? Sin theta is cos of pi over 2 minus theta. Agreed? So that is the angle between ket A and H. Theta is the angle between H and B. Pi over 2 minus theta is the angle between ket A and ket H. Agreed? So we take cos of that, which is the mod of the inner product between ket A and ket H. Agreed? Any question? See, we want to go like as slow as possible, okay, so that everybody is able to follow. So please, for anything you little bit unclear or anything, please stop and ask questions. Okay? This one, just take it as granted for now. Take it as a fact. Okay? You can try to do homework exercise for this. But for now, take it as a fact. Later we can also try to do in tutorial, but I am just saying for now. Okay? There are some things like this we will keep leaving for homework or for tutorials, right? So that we are able to maintain the flow of our argument. Okay? So that we are able to maintain the flow of our argument. Okay? So we can just for now take them as given facts. Okay? Fantastic. So now we are looking at the inner product between A and H. Now what is the inner product between A and H? You see, the number of places, let's go back to A and H. Okay? Firstly, from here can you tell me what is the inner product between A and H? Huh? Yes? Square root A over N. Agree? That's it. Correct? Yes? That's it. Square root A over N. Square root A over N. Yes? That is the inner product. So what did we obtain? Theta is like square root A over N. Theta is square root A over N. Number of iterations we take is, remember, let us assume that we are starting with a small theta. We have to go all the way to pi over 2. Agreed? Angle should be pi over 2. So this 2k plus 1 times theta should be approximately pi over 2. Okay? Now forget about this plus 1 and all, it is roughly 2k here. 2k times theta pi over 2. So roughly, if you think about, pi over 2 is also a constant. So theta is what? Theta is like pi over 2 divided by, sorry, k is pi over, like pi over 4, sorry, pi over 4 theta is k. Agreed? What is this? Forget the plus 1, okay? So 2k theta is pi over 2. So pi over 4 theta is k, approximately. K is pi over 4 theta, forget this plus 1 and all. Pi over 4 theta. But you can see that pi over 4 is constant. So k is order 1 over theta. You agree? K is order 1 over theta. What is theta? We just now n square root a. So order square root n over a, because that is a over n, capital N over a. Now, so even if small a is 1, okay, worst case you see, I have a single 1, everything else is 0. Small a is 1. That time also what am I getting? Square root n. So the number of iterations we have to do is square root n. In fact, if a is larger, we are only needing lesser number of iterations. Worst case still order square root n. See this? How and where is the square root n coming from? This entire square root business is because of L2 normalization, right? 1 over square root n. Why? Because we are doing L2 norm 1. If we are doing L1 norm 1, we will have 1 over n there. Because we square, remember in L2 norm we square. So this power of L2 norm, you see, reducing our number of iterations from n to square root n. Any questions? You can see the long press, then you can see the light.
Hello.
Yeah.
So you explained how do you calculate the inner product using this prerequisite that take cos theta as mod of this, and then you get this. But how do you actually calculate like from A and H, the inner product?
This one we found out, right?
I mean, you just put the values cos pi by 2 minus theta, that values you put, right?
Yeah.
But instead of that, what if you put the other way of doing it, like the actual way of doing the inner product between A and H?
No, this is the actual way only. We did the actual, this is the actual inner product between the two.
So like you said the inner, no, you said that cos pi by 2 minus theta, that is equal to the magnitude of inner product of A and H.
Yes.
Alright, so first of all, how, that is one question, and
What is the one question? Why is this?
yeah.
No. This I said we have to take it as a fact.
Alright, so if
Remember,
you take
this
as
I
a
said we
fact,
have to take it as a fact.
so
For now, take it as a fact. Angle, if you have two vectors, two unit vectors, then the angle between them, beta, okay? The formula is cos beta equal to the mod of the inner product between the two vectors.
So if you take that as a fact, I mean, okay, we understand that, but how do you actually calculate the inner product then? This is not the way, right? Because you have taken this as an assumption, and then you're saying this is the same as inner product. But so like
Yeah,
if
so
you
this is
if
the
you
actual
know A and if you know H, then how you would actually find the inner product? That's what I was asking.
if you know A,
Yeah,
if you know H,
yeah,
how do you find the actual inner product?
yeah.
Because of this relationship here. We have this relationship, right?
I mean,
Why the inner product between ket A and ket H is square root A?
by n, yeah.
Why?
Yeah.
Okay. You want to answer? You answered right. Huh? Okay. Okay, I will erase this one, okay? All right. We are calculating A and H, right? Yes? We just do the math slowly one by one. Don't, if you try to think too much, then we will not get it. What we want to calculate, write it, start doing the math. One by one, slowly, okay? Okay. That means A and what is this H? 1 over square root n square root A ket A plus square root B ket B. Agreed? Yes? Yes or no? Now, linearity of multiplication over addition. Linearity of multiplication over addition. Yes or no? Simply we take the multiplication inside the addition. Multiplication distributes over addition. Any question? Yes? What is inner product of A with A? It is norm 1, right? What is the inner product of A with B? They are orthogonal. Agreed? What is the answer you are getting? What? Yeah. No. His question was, why is the inner product between A and H square root small a over capital N? Now is it clear? Yes? I'm saying every time you like this, just start to do the math. If you just think like this, you won't get it. Do the math, step by step. Don't skip any step. Then you will get it. Okay? Okay. Any more questions? No, we can go slow here. Okay. I don't know whether when you are already speaking loud, maybe it's already getting recorded or not. I don't know. Maybe it is, but I don't know.
So I was just asking, all of the sudden, why did you choose of finding a big O of something? Because we usually don't do that, right?
No, because we want to estimate the number of iterations. No. We want to estimate the number of iterations we have to do. Because that is the that will determine number of times we have to query. We are doing this reflection, alternate reflections, right? We have to ask how many times we have to do this alternate reflections. Correct? Because that will determine number of queries we have to do to the database. We'll see that. Because we have to still see how do we do the reflections. How do we do the reflection about ket H? How do we do the reflection about ket B? Okay? How to do those reflections is what we will see now. But each time we do a reflection, this pair of reflection, we have to do, we will see, we have to query the database once. So therefore, we need to determine how many times we have to query the database. That is our cost, right? We are counting query cost. So we have to determine how many times we have to do the iterations. How many times you have to do the iteration? You're starting from theta, okay? Each time you're adding 2 theta, 2 theta, 2 theta. You want to go to pi over 2. So, something like k iterations, 2k times theta should be pi over 2, give or take. Agreed? 2k times theta should be pi over 2. That means k should be pi over 4 theta. Agreed? But pi over 4 is a constant, fixed constant, nothing to do with our input size. So forget about it. Now what happens? So whenever there is a constant, we put O. But the important thing is, now what is left? Theta. But theta can depend on n. Theta can depend on our input size, which is precisely what we are finding. The theta is turning out to be, theta is close to sin theta, which is square root a over capital N. Agreed? So theta has a dependence on input size. Agreed? Even if small a, worst case you say, even if small a is 1, theta will look like 1 over square root n. And number of iterations are like order 1 over theta. So number of iterations become order square root. But the important thing to grab is the square root n, not the constants here and there. In the asymptotic, the important thing to grab is the square root n, because we are looking at that quadratic improvement. Any questions? Did that answer your question, or? You have to start the mic. I think there is a problem with this mic. Maybe we can have another mic. This mic is closing all the time. Yeah.
Yeah, so I was just saying that that answered the question, but I was thinking that order of something gives actually a set, right? It gives a set of values. I mean, big O of, for example, n, it means set of values of n, n plus 1, n plus 2, like that, right?
No.
So like when we were studying asymptotic notations, we were
Yes.
told that order of something gives the set value. I mean,
Set of functions.
yeah, set of functions. Yeah.
Yeah.
So
So constant times square root n is big O of what?
square root of n.
Yeah.
Yeah, so basically k was a number, now it became a set.
K is a function of n. Remember, number of iterations will depend on our input size. Number of iterations will depend on input size. Remember, all the time when we are talking about running time of algorithms, when you talk about Deutsch-Jozsa, everything, we were always asking what is the running time or the query complexity of that algorithm, scaling as the input size, whether it's 2 to the n, 2 to the n over 2, square root n, constant, what is it? That is always we are asking, no? 2 as a function of the, as a function of what?
The input.
Huh? As a function of, I have a certain input size. What is my input size?
And
Huh? Number of bits in the database, how much it is? 2 to the power n, which we are calling capital N. So we have to determine how many queries we have to do as a function of capital N. Agreed or no? Yes? Yes? So constant times square root of capital N is order square root capital N. Asymptotic notation. Agreed? Any further question? Yes? Any further question?
And so why theta is also written as order of that?
Theta?
Like before we said theta equals sine theta is equal to root of a by n, right?
Yeah.
At that time we determined that theta should be equal to sine inverse of root a by n.
But remember, theta is close to sine theta for small theta.
Yeah.
So
still
take
the
theta
values are small, right? I mean, when you had declared theta equals sine inverse of root a by n, like
Yeah.
the first line, at that time also theta was small.
Yeah.
And when you're declaring that theta is equal to big O of this, still the value of theta is
Yeah,
small.
yeah, that is true.
Alright,
But-
so
but
that
I'm-
was a number and this is a set. Like that was root, like over there was theta equals directly equals sine inverse of root a by n.
Yes.
And now theta equals big O of sine inverse of root a by
No,
n.
no. Okay, you forget about this. Okay, forget about this. The fact that this is close to it. Okay, if something is close to it, that is. So if something is very close to it, you can also write theta is order of this. But forget about this. Okay, forget about this line. Focus on this line. Theta is close to sine theta. Agreed? Small values. But point is, we are typically looking at a situation where a is small. Because the worst case actually occurs when the number of ones is small. If the number of ones is large, then it's easier to find the one, right? So we are looking at the worst case performance of this algorithm where the number of ones is small. In particular, we are taking the extreme case when the number of one is exactly 1. Among 2 to the small n entries, you have a single one somewhere. That is the extreme worst case situation that we are considering, in which case theta is small, right? Because n is large. N is large, 2 to the n is large, therefore 1 over n is small, very small. Okay, even if n is 100, small n, 2 to the 100 is how much? Huge. Agreed? So 1 over 2 to the 100 is how much? Very, very tiny. Agreed? So in which case we will take theta to be sine theta. Okay? Theta to be sine theta. Sine theta is exactly equal to this. So take theta to be very, very close to this. And then 1 over theta will look like this. Agreed? Any questions? Yes? Right? Yes, yes. Square root n is also a lower bound for quantum algorithms for the search problem. Okay? Square root n is also lower bound. But that is harder to argue. Okay? That's a harder thing to argue. We will not argue that. We are focusing here on algorithms. Okay? Not lower bounds. But it is true. You can't do better than what Grover does. Okay? Pardon me? Log n running time. Yeah, of course it will be better. But you can't get it. It is not an ordered. If you have ordered database, you can do binary search. This is not ordered. You understand?
Best case is better. Best case is better.
Take the mic.
I was just saying best case is better.
What do you mean best case?
Best case of both of them if you compare. Best case of binary search would
No,
come
binary
out.
search is, you can't run binary search algorithm. Because you don't have the ordered database.
Yeah, so for best case we would have an ordered database.
Why will you have an order? The problem is the following. You are given any string in the database. There is no promise on the string. There is no promise that I've ordered the string this way or that way. I don't give any promise on that. And now you have to determine location of a 1. That is the task. The task is not as I have like ordered the zeros first and the ones later on. I have not done any of that. Okay? I am giving you in the database any string, just any string. And you need to determine the location of a 1. That is the task. If I have to order, it will take me time, right? Then I have to also count that time. So we are taking that off. Okay? The problem is that there is what we call unstructured input. This is unstructured search. Ordered search is a structured search where there is some structure available on the input. Okay? So the task is different. So we can't compare. This is not there won't be apples versus apples if we compare structured search versus unstructured search. Okay? Yes? Any more questions? Good? Okay. So now, let us proceed to understand how we are going to do the reflection about ket H and ket B. Before we understand that, let us understand what we mean by reflection by any vector ket U. Okay? Any vector ket U. Remember, we are talking about that plane. Okay? That plane spanned by A and B. I have any vector ket U there, and I am talking about reflection about it. Okay? So suppose I have any vector ket V, which I express as a linear combination of ket U and something orthogonal to ket U in that plane, which I am calling, let's say, U dagger. Correct? Agreed? I am calling that one. Actually, it is U orthogonal. Okay? U orthogonal. Okay? U orthogonal. Okay? Just take that this is the vector orthogonal to U in the plane. Okay? This is not bra U, huh? Don't take it as a bra U. I'm just calling that vector as with this symbol, okay? Maybe I can use a different symbol actually. Okay? But this basically it's the orthogonal vector. Okay? Good. Now, if I want to reflect V about U, what it means, okay, vector V is there, vector U is there. I have the orthogonal vector. Vector V I want to reflect about U. What does it mean? The U component remains the same and the orthogonal component becomes minus. You agree? Yes? Yes? Okay. I have let's say this situation, okay, A and B. We had A and B. I have some vector V here. Let me take it for the general case, okay. This is my U orthogonal, okay. This is U. What is the reflected one? Reflected one is this, correct? Okay. But what does it mean? It means I kept the U component the same and the orthogonal component I made minus. You agree? Yes or no? Okay. Let's take the special case. Suppose we are taking the vector in the space of 0 and 1. Okay, ket 0, ket 1. Just for example, I am saying. Okay. Ket V supposes alpha ket 0 plus beta ket 1. Okay? Suppose it like that. What is the reflected one? Let me call this reflected one as V1. Okay? V1 will be what? Alpha ket 0 minus beta ket 1. Agreed? This one would be, look, it has two components, this and this, right? This vector has two components. This one is the component around the direction of 0. So this is alpha ket 0, beta ket 1. What do? I keep this component the same. This component I reverse. Correct? Agreed? Huh? X-axis. If I have to reflect around x-axis, I keep the component on the x-axis the same. I make the y-axis sign negative. Agreed? That will be called reflection about x-axis. If I have to reflect about the y-axis, I keep the component on the y-axis the same. I change the sign of the x-axis. That will be called reflection about the y-axis. Agreed? Yes? Yes or no? That will be the definition of reflection. Yes. So now what are we doing? We are reflecting about u. When we are reflecting about u, we keep the u same, u perp we negate. Agreed? Yes or no? That is the RU. RU means reflection about u. Now, very interesting thing we can note. Very interesting thing. How do I write RU? RU I can write as 2 ket u bra u minus identity. Okay? Ket u bra u is a matrix. Now we are in the two-dimensional space, so let us say 2 by 2 matrix for now, because we are in the but as such we are not in two-dimensional space because we have all these 2 to the n things. But in the plane I am saying, if you focus on the plane. Nonetheless, you can write it like this. Firstly, why is this even a unitary? If you do RU times RU dagger, you should get what? Identity. For unitary, RU times RU dagger should be identity. So that you can check, homework exercise. Okay? If you want, I will do it now also. Not difficult. RU times RU dagger. What is this? 2 ket u bra u minus identity, right? Correct? What is RU dagger? RU dagger. What is that? 2 ket u bra u minus identity dagger. Agreed? That is equal to 2 ket u bra u dagger minus identity dagger. What is identity dagger? Identity. Correct? If you have ones on the diagonal and zeros elsewhere, what is the transpose? Identity only. What will be the conjugate? Identity. Because it has real entries. Now what is the dagger of this? Remember, A times B dagger is B dagger, A dagger. So 2 doesn't matter, 2 stays as it is. Brayu dagger, what is Brayu dagger? Huh? Ket U. Then what is Ket U dagger? So what are we getting here? Correct? Yes? Agreed? RU dagger is RU. No difference. Good. Okay. Now, this I multiply with, let me write a little bit shorter here. Agreed? Yes? This is equal to this times this. What is this times this? 2 Ket U, Brayu, Ket U, Brayu 4. Correct? Agreed? This times this. What is this times this? 2 Ket U, Brayu minus. Then what is this time this? Agreed? Yes? What is this? Identity times identity plus identity. Now, what is Ket U times Brayu here? Sorry, Brayu times Ket U? 1. So that will come out. It's a scalar. It will come out. You get 4. Ket U. This has come out. Brayu. Agreed? Yes or no? The inner thing became 1, came out. Then only the outer things are remaining. Minus 2, 2. Correct? Plus identity. These two cancel. What do you get? Identity. Agreed? Yes? So therefore, this is a unitary. Agreed? Unitary. Once it is a unitary, let us see what the action of this on Ket U is. Okay? Action of this unitary on Ket U. Any questions so far? Any questions so far? On Ket U, multiply RU with Ket U. So we are multiplying this unitary with 2 Ket U minus Ket U. RU times U perp. U perp actually it is. I am writing it as U dagger, but that is U perp. U perp. What is it? RU times U perp. What is Brayu times U perp? Brayu times Ket U perp. What is that? Huh? 0. Because they are orthogonal. This is 0. So the first term is gone. What is the second? Identity times this one. Minus. Agreed? Yes? So RU times Ket U is U, RU times U perp is minus U perp. Agreed? So therefore, if you apply RU on Ket V, U will remain as is because U go U. RU times this alpha times Ket U. RU times U perp is minus Ket U perp. So this will become minus. Once it becomes minus, we have obtained the desired reflection about Ket U. Agreed? because if we wanted to reflect about ket u, we wanted the sign of ket u to remain the same and the sign of u perp to become minus. That is what we have achieved using this unitary. So therefore, this is reflection about u. This unitary, which is 2 ket u bra u minus identity, is reflection about ket u, which we are representing it as Ru. Agreed? Just now we said, let us call Ru to be this. Let us call Ru to be this, and then we saw that this its action on u is it keeps u invariant, u perp it changes the sign. Therefore, it will take ket v to this, and therefore it is a reflection about ket u. Agreed? Any vector ket v will change like that. Any vector. Doesn't matter what alpha beta is. Agreed?
And the last one is it u per or u dagger? Or u per or u dagger?
U perp. This is perp. Maybe I should check the sign. I will call it something else. Perp. Maybe I will write PERP. Okay? Of Ru? Yes, eigenvectors are going to be ket u and ket u perp. Yes, and the eigenvalue will be +1 and -1. Agreed. Yes. Yes? Anyway, so this I will take care of. Okay? Alright, so we understood what is reflection about ket u. Now, let us understand reflection about all zeros. Let us understand reflection about all zeros. Okay? All zeros. Again, okay, if I have to do a reflection about all zeros, what do I need? I write any vector ket v as linear combination of all zeros and other vectors orthogonal to all zeros in the standard basis. Then reflection will mean I have to keep the component of all zeros the same and component of everything else to be minus. Agreed? Because this one is orthogonal to all zeros, this whole vector here. Agreed? That whole vector have to change the sign. So the whole vector, the sign changes. That is reflection about all zeros. Agreed? Now this one I can implement. Why? I have to just go and look at the value of x. Once it is all zeros, I don't do anything. If it's anything else, I change the sign. Correct? For this, I don't even have to look at the database. Correct? Because it has nothing to do with the value f of x. Simply x itself. X is all zeros or not. So in my circuit, I just do like, I can sort of do like or something like that to determine whether it's all zeros or not. Once I have determined it's all zeros, I leave it as it is. Anything else, I flip the sign. That one I can do. Okay. So this we can implement, this reflection about all zeros. No issues? Fantastic. Now reflection about ket h. Remember, in our algorithm we are doing this alternating reflection about ket h and agreed. We are doing this alternating reflection about ket h and ket b. So see how to implement ket h, reflection about ket h. We have seen reflection about ket h will be 2 ket bra h minus identity. Agreed? Just now we saw. R0 is reflection about 0, which is 2 ket bra all zeros minus identity. Agreed? Now we note one thing, right? H tensor and all zeros is ket h. Agreed? That is the formula. So now let's look at this matrix here. H tensor and R0, H tensor and. This unitary matrix. H tensor and R0, H tensor and. Remember, product of unitaries is Product of unitaries is u times v. If u is unitary, v is unitary. What is u times v? Unitary. Correct. If u is unitary, v is unitary. What is u times v? Unitary. This we have. U times v. Okay. U times v dagger. Correct. This is u times v. U v dagger is what? V dagger, u dagger. V dagger. What is this? Identity. What is this? Okay. So if u and v are unitaries, u times v is unitary. Therefore, this is unitary, this is unitary, this is unitary. Product is unitary. But what does it become? R0 is this, remember? Right? And we have H tensor and H tensor. We bring H tensor in, multiply with this ket zeros. What does this become? Ket H. Again from the right we multiply. What does it become? Bra H. Agreed? Yes or no? So we get ket H, bra H. That one is, this is RH. Agreed? So this unitary is RH. Okay? Correct. How do we do this then? H tensor n we can do. R0 we can do. So circuit will be, first you do H tensor n, then you do R0, then you do H tensor n. Combination will be reflection about H, ket H. Agreed? Yes or no? Any questions here? No, because we wanted to get this, no. We want to get this. How do we implement this? We are saying we can implement this by doing this. Hadamard followed by R0 followed by Hadamard. Yeah. Grover figured out the whole thing. Grover figured out the whole algorithm and the analysis. Okay. And this is back in 1995. 30 years already.
So you mean like just now we believed that RU was equal to 2 ket bra U minus I?
Yes.
Just like that we have to believe that the inverse would be Hadamard on both sides of R0, right?
Believe, why is it a belief now?
So because you said assume that for now RU is equal to 2 ket bra U.
No, that is, I didn't say assume. That is what we showed. That is not an assumption.
So but it started with an assumption, right? We didn't figure out that why we are doing that step, but we did that step and got to know that yeah, this was correct.
What step? I didn't understand.
I mean, when you chose that RU is equal to 2 ket bra U minus I, that time we were not knowing that this is the answer, but we just simply chose it and we found out it is correct.
Correct.
Yeah.
Agreed.
So it's a kind of assumption only, right?
It's not an assumption.
So if
Okay,
it
you
is
can
not
say that we did a guess first for RU, but then we verified. You can say that, oh, initially we guessed what should be RU, but then we verified. It's not an assumption anymore. After you do a guess followed by verification, then it's a proof. Great. Then it's not an assumption.
So similarly, R0 value like that Hadamard on both sides of R0, that is also a guess.
Guess followed by verification.
Yeah.
Guess followed by doing the math to verify. Once we have verified, then it is not an assumption. Then it's valid statement. It's an assertion. Then it's not an assumption. It's an assertion. Assertion means it's a valid statement. Correct claim. Correct theorem. Okay? Agreed?
So like, is there a way or a method of assuming or
that and all is requires experience. Yeah? And some amount of novelty, ingenuity and so on. So designing of algorithms will always involve experience and novelty.
so but can't it be explained by a simple logic instead of so much years of experience? I mean, after you have got it, maybe that there was a simple logic, right?
In retrospect, you mean? Like what did Grover think in his mind to guess this? No, I mean, maybe he stared at, this equation for a while, right? Right? And then he stared at this for a while, and then put 2 and 2 together. I don't know. This is just a very wild guess.
I mean, that is a valid thing, but there might be a simple logic. I'm not saying that it's just by staring it, but maybe something logical.
I leave it to you to determine. Now you have seen it, right? Now, do you see a simple logic here? What you would like to call simple?
I've not seen it enough, sir.
Huh?
I have
That's
not
what I'm
seen it
saying. That's what I'm saying. That's why you need experience, right? Agreed? Yes? The math is here. The entire math that is needed is here. Now you determine for yourself what is simple, what is this, what is that, how do you determine it. All that is a subjective thing you can determine for yourself. Okay? So now we have determined what is RH and how to implement RH in a circuit. And we have seen that this does not require any query to the database. Hash tensor and doesn't require any query to the database. R0 doesn't require any query to the database. So reflection about hash does not require any query to the database. Oh, by the way, so just now we used the fact that, you see, this one, hash tensor n times hash tensor n, right? That is identity. Why? Because, you know, h is hash dagger and h square is hash dagger h equal to identity. Agreed? Because h square is, because, right, h is hash dagger, so hash dagger h is which is identity because it's unitary. So h square is unitary. So now h times h becomes unitary, identity. And it is identity tensor n, which is identity. Agreed? That is simply I am saying why the second term is identity. First term we see is this. Okay? Okay. So this is how to do reflection about H. Now let us look at reflection about ket B. Okay? Ket B. Remember we are doing reflection about ket B, ket H, ket B, ket H. Now for this we will require query to the database. Agreed? What is happening? Now let us write ket B as alpha ket A plus beta ket B, any vector V in the plane of ket A and ket B with some coefficients alpha beta. What is the reflection about ket B? We have to keep ket B as it is, ket A we have to put a minus sign. Agreed? Reflection about ket B. So, how to implement that one? You see, look at this ZF. Let's define this unitary ZF. What it is doing? Minus 1 to the f of x, ket x goes to minus 1 to the f of x, ket x. Ket x goes to minus 1 to the f of x, ket x. This operation we have seen a few times already. Remember? How to get the value of f of x in the phase. What we are calling? Phase kickback. And we have seen how to implement that using BF. Remember? Always we have this extra wire coming at ket 1 and this kind of stuff and you know BF and then trash and everything. So using BF we could have implemented ZF. What is ZF? BF gives me the value of f of x in the extra wire. Using that we can do ZF, which is gives me the value of f of x in the phase sign, phase kickback. This we have using BF we can implement ZF using phase kickback. This we have seen a few times already. Therefore we can implement this, but this requires BF. One implementation of ZF requires one implementation of BF. Agreed? So each time we implement ZF, we need to implement BF. That means, and each time you have to reflect about, okay, wait a second, let me complete. So ZF is this, right, which is minus 1 to the f of x. Now you can see that ZF is precisely doing this operation. Why? Because ket B is where the f of x is what? F of x was what? 0. Precisely right. All the entries x where f of x was 0 was included in ket B. Minus 1 to the 0 is, so the sign will not change. Agreed? And A, what will happen? A, the value of f of x is what? 1. What is minus 1 to the 1? Minus 1. Sign will? Agreed? So if you act as ZF on V, what are you going to get? W. Agreed? So ZF is precisely the inversion about ket B. ZF is precisely the inversion about ket B. Correct? So this, see, it takes some observation. Again, we don't know what went on in Grover's mind, but Grover would have seen, Deutsch, and all, maybe, right? I don't know whether he did. Okay, this is just complete wild guess. But there, then he observes. Look, each time they are doing this minus 1 to the f of x, they are putting it in the face. That amounts to reflection about ket B. Correct? Then reflection about ket H, okay, I can do. Now let me have this algorithm. We don't know, I'm just saying. But it is always like this. You first look at literature, okay? You see what has been happening in the literature, okay? You try to make a good sense of that. Once you make a good sense of that, then you can put 2 and 2 together to produce new results. That's how typically research is about, right? You look at the literature, what people have done before, you try to make good sense. Once you can make good sense, you can put 2 and 2 together. Okay? So we see reflection about B, we see reflection about H. So that completes our analysis of Grover's algorithm. Any questions? Any questions? Okay, let us revise the whole thing one more time. Let us revise the whole thing one more time. What was our task? Our task was, we are given capital N equal to 2 to the small n bits in the database. We need to determine location of any single one. We can output any single one, doesn't matter which one. Any one, the location we have to output. That is the task. Okay. What is the algorithm? We define these vectors ket A and ket B. Capital A, the set of all x such that f of x equal to 1. Capital B, the set of all x such that f of x equal to 0. Ket A is the uniform superposition among all x in capital A. Ket B is the uniform superposition among all x in capital B. Agreed? Fantastic. So we consider this plane spanned by ket A and ket B. This ket H also we define, which is the equal superposition over all x. Fantastic. Then we note one thing. Ket H belongs to the plane of ket A and ket B. It can be written as this superposition. Correct? Okay. Then we note that we can create ket H, not a problem. H tensor n with 0n, n zeros. Correct? We can start with this vector. Then we will do this reflection about ket B, reach here. Then reflection about ket H, reach here. Reflection about ket B again, reach here. Reflection about ket H again, reach here. These alternate reflections. We are pushing our vector closer and closer to A. This time we are adding this 2 theta to 2 theta as we reflect. So we need to determine how many times we have to iterate. K is the number, but what is K? K as a function of theta. K as a function of theta. So because we are adding 2 theta each time and we have to reach pi over 2, K is like 1 over theta. Constant times 1 over theta. Pi over 2 and all doesn't matter. So we have to focus on what is theta, because then it will give us what is 1 over theta. Now turns out that theta is, because theta is small, theta is same as sin theta is square root small a over n. So 1 over theta is square root capital N over a. Square root. And why it is square root? Because our normalization is always L2 normalization. You see the difference? The square root is simply coming up because of the L2 normalization. Therefore, number of iterations is order square root capital N over A. Okay. Even if A is small one, it is order square root capital N. If A is more, it is even lesser. But we have to be careful of one thing. Point is, we don't know what is small a. Remember? We don't know how many ones are there. Correct? It could be large, it could be small. Point is, we keep going towards A, right? If we don't stop, we'll keep going like this. Then we'll go farther away from A. Correct? So we have to also stop. So this is a question we will do in tutorial exercise. Even if we don't know what is the value of small a, we should be able to stop at the right point. So that we can do, okay, by like, sort of geometrically increasing our number of iterations. Okay. So even without the knowledge of small a, we will be able to stop in order square root n. In fact, order square root n over a iterations. Even that people are managed to do. But in any case, order square root n we can manage. Correct? So that is one last component of the algorithm which we have not looked at here. Like, if I don't know what is small a, what to do? But if I know small a, I know what to do. Then I know how many iterations I have to stop. Agreed? Now what will happen? This vector will become very close to ket a after the number of iterations. Okay, very, very close to ket a. Once it becomes very close to ket a, what do? I just measure. Correct? How close? Meaning up to like 2 theta close. Right? I keep going, then after come here, then 2 theta it crosses here. If it crosses there, I don't do anything. Okay? But theta is small, right? So I'm very close. That time I just go ahead and measure. The probability that I will get something in ket a, something in a, will be very, very high. Correct? The error will be proportional to cos square theta, because it's very, very close, remember? Okay. But theta is tiny. So, sorry, the correctness, what am I saying? This vector has gone very, very close to a. Okay. So now let me call the angle between them as not theta, because theta is the starting theta, some alpha. But remember, alpha is very tiny. Okay. So again, remember, if I take a vector like this and another vector is very close to it, then if I measure this, I will get x in a with probability cos square alpha. Again the inner product will come into picture. So probability cos square alpha, but now alpha is very, very close to 1. So cos square alpha is, sorry, alpha is very, very close to 0. So cos square alpha is very, very close to 1. Okay? Agreed? Alpha is like 2 theta, so it's very, very tiny. Okay? So cos square alpha is very close to 1. So that will be the probability. We will get something belonging to A. Something belonging to B will be with probability sin square alpha, but sin square alpha is very tiny. Agreed? Yes? Yes? So Mike.
So fundamentally we are increasing the angle of our vector so that it reaches to that nearby A.
Yes.
And every time we are incrementing 2 theta plus 1.
Exactly.
So
No, 2 theta, not 2 theta plus 1.
that 2 theta, the total angle, 2 theta every time we are increasing.
Yes.
Fine. So, and that is not depending upon that 2 theta value. So the final order will be upon in the order of root n. So my thing is like,
Now,
if we increase,
final order is like 1 over theta.
so if we increase more than 2 theta in every
Yes.
step, then
We'll reach
our-
faster.
we will faster.
Yes. But we don't know how to do that.
Okay.
Okay. But in any case, there is a lower bound. So we cannot do anything better than that. Okay.
Can we go to the task? So here we are actually finding one bit. Among
Any one,
2 to the power n, only one is bit is there, rest are zeros.
No. That is not true. I'm saying you can have any function f, which means you can have any string in the database. Any places you have zeros and one, zeros and one. That is what is given to you. But I'm just saying that the hard instances of that problem are captured by. It is not that those are the only instances that are given to us. All I'm saying is the hard instances are captured by the fact that everything is zero except there is a single one. And we don't know the location of a single one.
So what
Those are
happened?
just the hard instances. But I'm not saying that they're the only instances that are given to us. It's not a promise problem. It's not that there will be the only instances given to us. Okay? Those are just the hard instances.
So for any given string combination of 0 and 1,
Yes.
it will figure it out that positions of 1 in
Any one's position.
any single one.
Any single position where 1 is written.
Okay.
Okay? Let's say 1 is written on the 70th position and the 93rd position and the 57th position.
Okay.
Then it will either answer 57, 93 or 70 like that.
So if I have, let's say, 10 ones in that string,
Yeah.
and then I have to figure it out the position of all ones.
All ones.
Like 10 ones I have, that I know, and remaining are zeros, and I have to figure out the position of those ones.
Yeah.
Then
You
we
can
have
also
to
do
run
like
it
that.
10 times.
Yeah, you can do like that. What you can do is first figure out the first position, okay? Then you assume, suppose you figure out the position 70. Then you assume that what is written in that position is 0. So every time you have to query 70, you don't query 70, you just write 0 there. Okay? Correct. You sort of artificially change your string in the database.
Okay.
Okay? Then your answer will not be 70 anymore. Something else.
Okay.
You pick that. Again make it 0. Pick that, make it 0. You can keep doing this.
So I was wondering if I can use this algorithm to find out the solution of any classical algorithm. Let's say we are solving knapsack,
Huh.
and we have n number of items,
Yes.
and I can represent those n number of items with an n number of strings.
Yes.
And my final solution will be a selection of ones, anything. 0, 1, 0, 1 represents, I will choosing one item or not, like that.
Yes.
So that thing we can represent as our solution.
Yes.
And I can run this Grover algorithm
Yes.
to figure it out that possible solutions among these values.
See, if you're trying to compute knapsack, right? Sorry, can you remind me what the problem knapsack?
Knapsack problem is like we have a number of items,
Yeah.
and every item has some value,
Yeah.
has some weight,
Yes.
and we have a constant on weight that our weight should not be exceed over the capacity,
Yes.
the collection of all the items weight.
Yes.
And our objective is to maximize the profit we are getting from those items.
Yes. But then what you're doing, you're just looking at the sum.
Mhm.
Correct? Correct.
So-
You are trying to maximize the number of entries you can take as long as the total sum of the weights is
Less
at
than
most your upper bound.
yes.
Now, if you want to solve this using Grover, what do you want to do?
Ultimately, what we are trying to do it, generally we do it, we can make a vector, and that vector is combination of zeros and 1. So let's say I have 10 item. So I have a bit of 10 string that is 0 or 1.
No, the number, usually your number of items will be large, no?
That's fine, but just an example. Let's say I have 10 items.
Yeah.
So the output string, I have 10 bits. And the position where I have 1, every position of the bit represents that item. The first item is linked to first bit, second item, second bit, like that.
Okay.
10 item.
Yeah.
And whenever we have 1 in that string, I say that I choose that item. And
Okay.
where we have 0, I reject that item.
Yes.
Like that.
Yes.
So we can have a possible candidate solution, a combination of zeros, 1, 1, where we have 1. Let's say 1, 3 and 7 we have 1.
Yeah.
So those item I picked and remaining item I don't pick.
Yes.
Like that we can have. So if any solution exists by the combination of these items, can I apply the Grover algorithm to find out the positions of ones and then verify, okay, this is
No, see, Grover's algorithm can only be applied when you should be able to query the value, like if I query the value f of x, I should know what is the value of f of x. You understand? If I query the database on location 50, I should know whether it is 0 or 1. Okay. Now, if it requires me some computation to determine whether it's 0 or 1, then that computation overhead will be there.
that's fine.
You see what I'm saying? What you can, if you just have to figure out whether it is 0 or 1 or the location of that, here remember we are assuming that our query is unit time. That is, if I go to the database, if I say what is written on the 57th entry, I get an answer in unit time, right? Because that is what we are counting. If it is also taking me a lot of time to find that out, which could be the case in knapsack or whatever, I don't know, depends on your reduction, then that overhead will be there. That overhead we are not taking care of in Grover's algorithm. Grover only is telling us that if I take that as unit time, then number of queries I have to do will be square root 10. But it is the case that Grover's algorithm is used as a subroutine in many algorithms, many algorithms. Okay? Especially to boost the probability of success of algorithms. Okay? You can get a quadratic boost compared to it's classical. Sometimes, in order to boost the probability of success, you do classical repetitions and take majority, right? There you can do Grover and you get quadratic boost there.
So in a typical solution, we can do some classical pre-processing, take the quantum boost, and then we can do some post-processing to combine all those things. That
Yes.
kind of algorithm we try to write down
We
by
can have.
using this thing.
We can have that.
Okay.
We can have that. Okay? Like Grover can be used as a subroutine in other algorithms, where the pre-processing, post-processing could be classical, could be quantum.
So here x is a n-bit string, na, in this problem
Yeah.
statement. So, but we have a string of length 2 to the power n, where we are trying to find whether.
Yes, so x represents the location.
Okay.
X represents the location. There are 2 to the n bits.
Okay.
X represents whether I'm querying the 57th location or the 73rd location or the 90th location. Okay? It will give me the value. X is the location, f of x is the value. X is the location on the database. If x is 57 in binary encoding, then answer is what is written on the 57th location.
So first reflection is we take A and B,
Yes.
and then we are reflecting over V1 after that.
This one.
Yeah, first we reflect about B, then
Yes.
we reflect about 1.
No, about H. Yeah,
About
V1.
V1.
Yes.
Yeah. So when we reflect about V1, are we changing the basis of V2 or
No, we are always working on this plane. Always on this plane.
okay,
Everything is a linear combination of A and B.
okay,
We are never going outside the plane. Okay?
yes,
We are never going outside the plane. So, in our recalling of everything, we reach the fact that we do like this. We scroll down. Then how to do these reflections? Okay. How to do a reflection about U? Then we saw RU does the reflection about U. Ket bra U minus 2 ket bra U minus identity. So reflection about R0 is reflection about 0 to the n is we have to implement this.
okay,
But how to implement this? This should be easy, right? We just have to figure whether x is all zeros or not. If x is all zeros, we don't change the sign. If x is anything else, we change the sign. So this we can do. So that means we can do R0, which is get all zeros minus identity. So how to do RH? RH is we observe this equation, right? And therefore this becomes h tensor n 2 ket bra all zeros minus identity h tensor n. H tensor n comes inside both sides becomes 2 ket bra h minus identity. This is RH. So we can implement RH, which is simply you do h tensor n followed by R0 followed by h tensor n. That is going to be our circuit. So that implements RH. How to do ket B? For this, we note that ket B requires, if I write any vector ket B as alpha ket A plus beta ket B, we need to change the sign of ket A. But that is done precisely by ZF, right? Which implements ket x goes to minus 1 to the f of x ket x. Because for this anything x f of x equal to 0, sign will not change. Anything x f of x equal to 1, sign will change. So ZF is something that precisely implements this reflection, correct? And how to implement ZF? Using BF, phase kickback, correct?
So sir, reflection about B will only happen if f of x is equal to 1.
No. Not reflection about B will only happen. This is going to happen for every x.
No, yeah, it won't happen if f of x equal to 0. Okay, yeah. If it is f of x is equal to 0, reflection will happen.
No.
No.
Minus sign will get in. If f of x equal to 0, the sign will not change in front of ket x. If f of x is 0, sign will not change in front of ket x. If f of x is equal to 1, sign will change in front of ket x. Agreed? That is the operation that is done for all x in superposition. You agree? It is not that this is for all x, not only for some x. Maybe I should put the symbol for all here, okay? This is for all x, not just some x. For all x, this is the operation. This unitary acts on all x, right? Because that is the entire computational basis. So we have to give, when we specify a unitary, we have to give its action on all the computational basis vectors. Agree? This is the action. Correct? All good? Any questions? Is a Grover?
So can we say that RU is a Grover coin? Here?
Grover
coin. Coin matrix is like that. Hadamard coin, like we represent as a coin matrix.
coin.
Yes.
Grover coin.
in graph we represent by 2 by d j minus I, which is a Grover coin. So I'm just thinking it's a Grover algorithm, so it must come from here. So I'm thinking so here it is like RU Grover.
You are trying to relate to some random walk algorithms?
Yeah, walk, yes sir.
Huh?
No, quantum walk. Yeah,
Quantum walk algorithms?
Yes sir.
Yeah, maybe that is the notation they use. Grover coin. They use the similar.
Yeah, not exactly, but it's a in there. Grover coin is a 2 by d j minus I, where j is a all entries are 1. So which represent as a Grover coin matrix.
2 what?
2 by d is a degree of the graph, and j minus I.
What is J?
J is a all 1 matrix. Every entries are 1.
Oh, yeah. That is also Kedbra. That is the Kedbra
Yes,
all
sir.
ones. No?
So that model is based on Grover algorithm. So
Yeah.
I'm thinking here like which notation is a Grover coin we can like.
Yeah.
Is it-
Yeah, there is a connection. Yeah, you can see note the connection. Yeah. But now you can see that we moved from promise problem to a total problem now. Why total problem? Because there was no promise on the input. Input could be anything. But now you see we got the advantage, quadratic advantage only. Earlier we were even getting exponential advantage. Here we got quadratic advantage. Right? Next we will move to Shor's algorithm. That is also a total problem, not a promise problem. There also we will see okay, advantage. See here it is a provable advantage, in the sense that classical must take omega of capital N, correct? And quantum takes order square root n. In the Shor's case, we believe, or we don't yet know of any classical algorithms which take polynomial time, but we will see a quantum algorithm that takes polynomial time. Okay. So the hardness of that problem is a conjectured hardness. We believe that, or we don't yet know of any algorithm which can solve it in polynomial time. In fact, that is what a lot of these RSA crypto systems are based upon. Okay. So we will get into that from subsequent lectures onwards. Okay. For now we finish Grover. If there are no more questions, we take a break for lunch. That if there are two vectors, okay, V and W, okay, let's assume their unit norms. Then if the angle is theta, then we said we wanted to confirm is the mod of the inner product, right? Agreed? Yes? Anybody wants to do this? Try this. Anybody wants to try this? Yes? Anybody? Okay. Yes? Okay, let's do that. Okay. So, let's consider the case of the plane 0 1 plane. Okay. Anyway, we in order to talk about the two vectors, we can talk about the plane of the two vectors. Let's take the 0 1 plane. We have a vector here. Okay. Let's call this vector V. V is alpha 0 plus beta 1. Agreed? Some vector. What do we have now? Projection of V on 0. So, this vector, just this vector plus this vector, you see there are two vectors like this. Just this vector is alpha 0. Agreed? This vector is, so alpha 0 plus beta 1, alpha 0 plus beta 1, we reach here. Agreed? Yes or no? Good. Now theta, right? What is cos theta? Cos theta is supposed to be base by hypotenuse. What is the base? Mod alpha, length. What is the hypotenuse? Mod alpha square plus mod beta square, but we are taking norm 1. Correct? We are taking norm 1 vectors, right? Mod alpha square plus mod beta square equal to 1. So cos theta is, agreed? Yes? What is the inner product of 0 with V? What is the inner product of 0 with V? 0 with alpha 0 beta 1, correct? From linearity, alpha 0 0 plus beta 0 1, that is equal to alpha, correct? So what is the mod of the inner product? That's what we got. There are two vectors. This is 0 unit vector, but this is going till here. The unit vector 0 is going till here. Okay? This is ket 0. This is alpha ket 0. This is V. So the inner product between ket 0 and V is alpha. So mod is mod alpha. But that is also cos theta, which is also the angle between 0 and V. And both are unit vectors. 0 is also unit vector, ket V is also unit vector. Clear? Any questions? Any question? We are doing the same argument but thinking of ket W as 0. Same argument but thinking of ket W as 0. Doesn't matter the translation. Correct? Translation doesn't matter. Any questions? Yes? Okay? Okay. Now, in Simon's algorithm, there was another thing. No, not in Simon's algorithm. This, I think, 1 out of 4 that algorithm, right? We said that we have these 4 orthonormal vectors, right? Remember? These 4 orthonormal 0, 0, 0, 1, 1, 0, 1, 1. Remember? Minus sign is at different places. There it is with 1, 1, there it is with 1, 0, there it is with 0, 1, there it is 0, 0. And we said these are 4 orthonormal vectors. And here is a circuit which can distinguish. Correct? Yes? We said that. This question is asking to confirm that. Show that the following circuit distinguishes the 4 states. Here the gate consisting of a single circle labeled -1 is the phase flip gate. Correct? And the control phase flip. Can you argue that this is the circuit that distinguishes the 4 states? Can you argue that? Okay, one by one. Take 500. Take 500. Apply this circuit. What is the output? Who wants to do that? Input is 500. Apply the circuit. What is the output? Who wants to do that? Volunteer. This one is systematic only. Just keep doing, right? It should happen. This we have seen a few times already. Correct? Who wants to do this? Volunteer. See, the purpose of tutorial is interactive, right? We don't want everything to be one directional. Only me lecturing all the time. Correct? Purpose of tutorial is practice. Practice is best if we have volunteers. Then they do, and then we can guide also. Okay, we can do it together. So we need volunteer for this one. Who has not come before? Huh? Anybody who has not come before? You want to come? Huh? Come, doesn't matter. Come. We can do it together, don't worry. You want to come? You have done it before? Come. Come. Just simply take 500 and, or even simpler, I am telling you, take 0, 0 as the input, see where it is going, map 0, 0, see where it is going, okay? Erase everything, you can erase. Just map 0, 0 and see where it is going, okay? Very simple. Draw the line in between, Yeah. Take 0, 0 and see where it is going. No, no, not 5 0. Just take 0 0. Ket 0 0. Under this circuit, okay? Here is the circuit. This is the circuit. No, circuit is this. Yeah, you're doing right. Pardon me? Yes. Yeah, apply the Hadamard gate. Apply the Hadamard. Apply the Hadamard on both the zeros. You can erase the middle line if you want. You don't want the middle line, you erase. Yeah, apply Hadamard on the both the zeros. No, 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 no. Don't do this matrix multiplication. Write in the Ketbra notation. Write in the Ketbra notation. Where does the Hadamard take? Where does the Ket 0 go under Hadamard? Yes. You guys can help him also. Just tell him how to do. Zero zero, where it is going? 0 0. No, don't write 0 0 equal to. Write 0 0, then write Hadamard tensor 2. Or write arrow. Put arrow. Put arrow. Yes. And here you write the gate you are doing. This is Hadamard tensor 2. Done on this. Where does this go to? Okay. Good. Okay. Right. Now, what happens when you do -1? Do the gate now. Now do the gate -1 gate you do. That one. -1. What will happen? What does that phase flip gate do? Huh? What does the phase flip gate do? It's not control. There is no control there. No, that is control phase flip. We are talking about only phase flip. only phase flip will do what? Only phase flip will do what? Okay. Phase flip gate flips the sign of 1. 0 it doesn't change. Got it? Only the 1. Now let's do that. No, don't write matrices. Here we have to use Cadbra notation. No vectors. Everything has to be in the Cadbra notation. What will phase flip do? You tell him, no. Tell him, help him. Ah. Right arrow. Yes. Okay. That happened. Now do control phase flip. You see, you have to do gate one by one. -1 done. Now control -1. Now you do control -1. What will happen? You got it? Control phase flip done? Okay, now do the two Hadamard's. Do the two Hadamard's. What? Okay. The signs are correct, is it? Huh? 0 and 3 minuses. That is correct? Huh? Okay, then you have to apply Hadamard's on everything and check. Correct? Yes. Yes. Control phase flip. No, control phase flip will only flip the sign of 1 1. Only flip the sign of 1 1. Okay. Now apply. Yes. You can do little bit shortcut if you want. No, cannot. Okay, something like this. This is there, right? This is there. Now, half ket 0 ket 0 minus ket 1, correct? Agreed? Then there is a ket 1 ket 0 plus ket 1. Agreed? Agreed? Now this will go to Hadamard tensor 2, right? This goes where? 0, correct? Actually there is a shorthand you guys can use, but doesn't matter. Where does this go to? 0 minus 1, where does it go to? Ket 1, correct. But there is square root 2 here. So, let me write it this way. Okay. This will go to, correct? This goes to, agreed? This goes to, correct? Yes? Now you simplify this. What is this? Okay, I have to erase this now. Okay. Correct? You got this? Yes? Yeah? Yes? Eventually, where did it go? The whole thing 0 0 went to here. Agreed? Finally, what happened? 0 0 on the application of the total circuit went here. Agreed? Okay. Now, you have to see where 0 1 goes to. Correct? Okay. Then you have to see where does 0, 1 go to. 1, 0 go to, 1, 1 go to. Okay. Once you have all the 4, then you can see where those individual vectors are going to. Okay. I tell you, there is another method, easier method. Easier method is, you see, we want to argue that those 4 vectors, where they are going, right? I tell you, you try to do an easier method. Look at where does C go to, where does 0, 0 go to on C inverse. That is, if 0, 0 is fed in from here, not from here, but from here, where does that go to? Okay. If, for example, you find that there are 4 vectors, all of them go to those initial vectors. 0, 0 go to 5, 0, 0, 0, 1 goes to 5, 0, 1, 1, 0 goes to. If that happens, then already you know that 5, 0, 0 will go to 0, 0 on the circuit. If 0, 0 on circuit inverse is going to 5, 0, 0, then 5, 0, 0 will go to 0, 0 on the circuit application. Okay. So, it is actually the case that you can verify that if you feed in 0, 0 from here, okay, then what will come out here is 5, 0, 0. 0, 1 from here, 5, 0, 1. 1, 0 from here, 5, 1, 0. 1, 1 from here, 5, 1, 1. Which means 5, 0, 0 will go to 0, 0. 5, 0, 1 will go to 0, 1. 5, 1, 0 will go to 1, 0. 5, 1 go to 1, 1. Got it? That is how you can then, because once it goes to 0, 0, 0, 1, 1, 0, 1, then you can go ahead and measure and you have the output. Right? 5, 0, 0 goes to 0, 0. Measure, output is 0, 0. 5, 0, 1 goes to 0, 1. Measure, output is 0, 1. So this way you can distinguish the 4 states, orthonormal states, using this circuit. Okay? This is little bit more involved example. But just still it is not a big circuit, you see. 2 by 2 few gates. Okay. Okay, thank you. Okay, now let us do this question, okay. This question. Remember in Simon's algorithm, we said that if we have these, remember what was happening in the Simon's algorithm? Suppose there is a hidden string S and you can uniformly sample strings Y satisfying S dot Y equal to 0. You want to find the hidden string S using only such samples. Suppose you can draw n minus 1 samples Y1 through Yn minus 1. Each of these Y1s are now n bit strings. Remember that was what was happening in Simon's algorithm. So we have all of these n minus 1 equations. Question is, under what condition is this enough to determine S? Assume that S is not equal to all zeros. Okay. So that we said was, if these equations are linear independent, we can go ahead and solve. Correct? And why n minus 1? Because remember we are saying S is not all zeros. That means S is orthogonal to all zeros. So therefore it kind of lies in an n minus 1 dimensional subspace because it's already orthogonal to. Therefore n minus 1 equations are enough. Okay? Because we know that S is not all zeros. But that is one thing. Second thing, given that the sampling of Y's is uniform amongst all strings that satisfy Y dot S equal to 0, shows the probability with which the condition in part A is satisfied is at least this product. Okay? So let's try to do this. Remember what we wanted to argue? That if we are lucky and if all these equations are linearly independent, then we can go ahead and solve. And we claimed that this happens with probability at least 1/4. And that is what we are trying to see here now. In part B and C, we are trying to see that the probability that all these equations turn out to be linearly independent is at least 1/4. Agreed? Okay. All right. I need a volunteer. Yes? You want to do it? Okay, you come. You come. Yeah, please raise the one. No, don't worry about this difference between n minus 1 equations and n variables, because we are promised that S is not all zeros. So that will also suffice. But now the question is this, okay, here is the question we are asking. We get the first equation, okay. What is the probability that the second y2 that we get, okay, is linearly independent of y1? You see, we obtain some y1. What is the probability that the y2 that we get is linearly independent of y1? In other words, it is yes. In other words, it is exactly, very correctly written. Okay. Now these are n-bit strings, which basically means that y2 is different from y1. See, one thing firstly we can see that the total number of strings which are satisfying this equation y dot s equal to 0, that is they are orthogonal to s. How many such strings are there? Suppose s is not all zeros. How many such strings are there? Huh? No, no, no. These are n-bit strings. They are all n-bit strings. How many total strings are there? 2 to the power n. Now we are saying how many strings are there such that y dot s equal to 0. Huh? Yes. How many strings satisfy s dot y equal to 0? How many y satisfy that? Huh? No, totally how many strings are there? 2 power n. Okay, I give you an example. Take s to be 1 and all zeros. Take s to be 1 and all zeros. How many strings satisfy y dot s equal to 0? Huh? How many strings satisfy s dot y equal to 0? Hmm? 2 power n minus 1. Because this should be 0, remaining can be 1 or 0, 1 or 0. Correct. Now let us take example. S is 101 all. There only you can change it. 101 all zeros. How many strings satisfy this? S dot y equal to 0. Have to be 0? Correct. How many strings are there? Very good. How many are there? Again 2. Okay, now let me give example. S is 1 0 1 1 and all zeros. Now how many are there? By 2 power n minus into 3 into 2, that is 2 to the power n minus 2. You do one, erase everything. Erase everything. Everything you erase. Okay. Write S equal to 1 0 1 1 all zeros. Now how many strings are there? Write all possible strings in the 3 locations which are giving you 0. The other matter, forget it. 111. What will 111 give you? 1.1. Dot product we have to do, right? All 0 you make. Okay. Yeah. So you no, which one are you writing? No. You have to write all possibility. Which one? You write one by one. You write possibility. What writing? No, not 8 possibility. The possibilities which are giving you dot product 0. No, don't do any shorthand. Just write all possibilities. First, just write all possibilities. Huh? Three cases. What about 0, 0, 0? Correct. How many cases are there? Huh? Is he? So are we getting some pattern here? It's always 2 to the power n minus. See? So therefore, just erase all this and write if S is not equal to all zeros. If S is not equal to all zeros, then number of y's satisfying y dot S equal to 0 is 2 power n minus 1. Agreed? Very good. Now suppose we have chosen y1. Okay. Now we are asking how many 2's are there? Okay, write y1 y1. y1. We are asking how many strings, okay, how many strings are in the span of y1? Of course, span of y1 and 0. Huh? see the way we are functioning is, okay, okay. See, here everywhere we are working in zeros and ones, the binary field, agree? So, when we multiply this vector by 0, we do entry wise multiplication. So, it takes us to the all zeros vector. Okay. See, whenever we are in a vector space and we ask so here we are asking, basically think of it this way, the span of y1 and 0 to the n. Take you to either y1 or to 0. Correct. So, as such, the span of y1 will have only 2 vectors. Okay. So, how many vectors are outside that one? Huh? No. All among all the vectors, all the y's, the 2 to the n minus 1 y's, right? How many are in the span of y1? 2. Agreed? So, I am saying, what is the probability that when you randomly sample a y, it is not among y1 or all zeros? You understand what I am saying? Look at all the strings y, there are 2 to the n minus 1 of them. I am randomly sampling one of them. Agreed? What is the probability? It is not all zeros, it is not y1. Okay, what is the probability that it is either all zeros or y1? Huh? Exactly, fantastic. Okay, now erase all that and keep this number with you. Yeah, this number, only keep this number. No. Didn't have to erase all top of it. But okay, you erase, okay, it doesn't matter. Once you erase it, doesn't matter. Just erase everything. Erase everything. Okay, doesn't matter. Erase everything. Right. Now, no, even the bottom and all you erase. Just write right there on top. Probability y2 is not in the span of y1 0, y1 and 0, if you want to put it, y1 comma 0. No, y1, okay. Not a is equal to, right, equal to 1 minus, okay, 2 over, correct? Yes? Now, what is the probability that y3 is not in the span of y1 and y2? Write that one. Probability y3 is not in the span of y1 and y2. How many vectors are there in the span of y1, y2? Huh? What about y1 plus y2? What about y1 plus y2? See, y2 was not in the span of y1, correct? So y1 plus y2 should be different from, it should be a different vector, correct? Write y1 plus y2. So there are 4 vectors in the span of y1 and y2. Yes, always y1 plus y2 mod 2. It will always be mod 2. Like that. You can call it bitwise parity. Agreed? So, what is the probability? Write the probability is equal to 1 minus what is the numerator? Yes. Agreed? Yes? Agreed? What is the pattern you are getting now? Not, don't call that also n. Suppose you have chosen k vectors. What will be the probability? Once you chose 2 vectors, what was the probability? Now k vector, what will be the probability? Correct? Correct? What is this the probability? That the next vector is not in the span of previous. Next vector is not in the span. That means you are keep on getting linearly independent equations. Once something is not in the span of previous, it's a linearly independent equation. Agreed? Yes? Fantastic. Now write the product. Start from the first term, second term, third term, just write the product. Now what is the first term? That is the first term. No, that one. These terms. You multiply now. No. The k will go up to all the way to it will go only up to n minus 2. See, n minus 1 if it goes, then it will become n minus 2, just write n minus 2 there. Yes. Agreed? This is the thing. Now erase everything on top, just keep the last one, erase everything on the top. Okay? Keep the last one. Yes. No, erase all that also. That and all. Very good. Now this is, what is the last term you see? Half. 1 minus half. Correct? So write in the reverse order. 1 minus half, 1 minus 1 over 2. No, write the first term 1 minus 1 over 2. Write it like that. 1 minus 1 over, no, first term, write 1 minus 1 over, 1 minus times 1 minus 1 over 1, 2 square, like that it will go all the way to 1 minus 1 over 2 power n minus 2. Agreed? Yes? This is the probability. Now I am saying, right, this is greater than equal to, right below greater than equal to 1 minus 1 over 2 bracket, close the bracket, 1 minus 1 over 2 square, close the bracket, go all the way up to infinity, 1 minus 1 over 2 to the power infinity. Agreed? Yes or no? That one is greater than this one. Yes or no? Because that one you are stopping at 2 to the power n minus 2. After that we are continuing with another some terms, but all of them are less than 1. So we can multiply to make it smaller. Agreed? Okay. Now I will tell you one thing. There is one formula. Remember, we are talking about these numbers in what range? From 0 to half, the one that we are subtracting. Okay, so there is a formula, 1 minus x, write the formula by the side, 1 minus x greater than equal to 4 minus x, 4 to the minus x, 4 to the minus x for x in the range 0 to half. For x in the range 0 to half, okay, including 0 and half, okay. Let us take this granted. Now what is the final one? 1 over 2 to the infinity is 0, agreed, and 1 minus 1 to the half. So this becomes greater than, use this formula, this is x, right here, greater than equal to 4 to the, what should be? Minus half. Correct. What should be this one? 4 to the? Minus 1 by 2. All the way up to? 2 power infinity is 0. 2 power infinity is infinity, so 1 by infinity is 0. Okay? Now accumulate all the terms in the numerator. Accumulate all the terms in the numerator, in the exponent. In the exponent, what are you getting? Correct. All the way to? Okay, what is this? This is a geometric series. What is the sum of this geometric series? You can erase everything on the bottom. Erase everything on the bottom. What is the sum of this geometric series? Okay, write that one. What is that? Remember? This is what we wanted to show. Agreed? That the probability that we will get all of the equations linear independent is at least, that is what we got. Agreed? And that one you can verify by actually looking, even plotting the graph of 1 minus x and 4 to the minus x. Okay? Agreed? So we see this. But it is so nice, you see, there are n equations. N could be a million, a zillion, a billion, whatever. but all of them will turn out to be linear independent is 1 by 4. Correct? That is what our analysis shows. Because eventually it becomes this sum of geometric series which converges to 1. Any questions? Any questions? Okay, so I think we have passed time, huh? So we can stop here.